Most weekend hikers step right over it, a glossy pebble no bigger than a thumb, half sunk in gravel. Yet under a 10x loupe, its vitreous luster and sharp, shell-like fracture pattern mark it as something far harder and far more valuable than river-rounded quartz. The missed opportunity is simple. Few know that some of the world's most overlooked gem candidates don't sparkle in the sun. They hide under a skin of dust, bruising, or age-worn polish. The key signal here isn't brilliance. It's fracture. Conchoidal, meaning curved and glass-like, is a break pattern shared by several high silica materials: quartz, jasper, agate, chalcedony, and even rarer ones like obsidian or common opal. These breaks tend to run smoothly, like the inside of a clamshell, and suggest a uniform internal structure. If it glints under low-angle light and feels heavier than it looks, it's not just another landscaping pebble. But hardness separates the mundane from the market-worthy. Quartz ranks a 7 on the Mohs scale, enough to scratch most glass. A field test involves dragging the stone edge across an inconspicuous bit of window pane, or better, a small glass tile, at a 45-degree angle. No powdering, no crumbling. Just a clean, confident scratch line? That's a start. But it's not conclusive. Glass itself is a deceptive reference, too variable, sometimes even harder than the sample. Instead, compare weight. A heavy-feeling rock for its size often signals higher density, nudging into jade or garnet territory. Use a water displacement test. Weigh the stone dry, then submerged, and compute specific gravity. Jadeite, for example, runs 3.3 to 3.5, nephrite about 2.9 to 3.0. Quartz lags at 2.65. The field version just means this: if two stones the same size feel noticeably different in weight, the denser one deserves a closer look. Luster is another tell. Vitreous, like broken glass, is common. But waxy or greasy luster, especially in greenish stones from serpentine-rich areas, may indicate nephrite jade. Adamantine, the highest shine short of metallic, is rare, seen in diamonds, zircon, and a few high-index fakes. If all this feels subtle, it is. That's why gem hunters learn to slow down in high-flow areas where water naturally sorts by density. Not every shiny stone is valuable, but every valuable rough stone hides behind a common disguise. What's next is decoding which ones reward the effort. A dull gray surface can fool even trained eyes, but a single wet swipe or a careful slice can reveal gem-grade interiors hiding in plain sight. It's a common field mistake, discarding a rough specimen because it lacks color or clarity at first glance. In reality, many valuable materials, like opal, agate, and jade, only show their true nature once surface oxidation, weathering rind, or fracture dust is removed. This becomes obvious during slabbing or polishing. One of the most transformative steps in lapidary work is the initial cut on a trim saw. Stones like moss agate or plume chalcedony can appear brown, crusted, or nondescript externally. But once cut, they reveal intricate inclusions, iron-stained tendrils, dendrites, or flame-like patterns, locked inside a translucent silica matrix. It's these hidden visuals that drive both value and desirability, especially in jewelry applications. Polishing completes the reveal. Using progressively finer abrasives, starting from 220 grit and advancing to 1200 or higher, a field-cut slab can be turned into a high-gloss cabochon or window. Opal, for instance, may show no play of color when dry and dusty. But with careful sanding and a polishing compound like cerium oxide, a flash of red, green, or blue emerges, often dictating whether it's common opal or precious. In jade, the transformation is even more dramatic. Nephrite and jadeite both suffer from surface staining, often making them look like dirty river rock. But under polish, nephrite takes on a waxy to silky sheen. Its unique fibrous texture diffuses light in a way no other stone does. Jadeite, denser and more granular, polishes to a glassier finish. Even low-grade jade can look dramatically better after surface cleaning, though serious collectors look for internal translucency and color uniformity, not just surface gloss. Field collectors use this principle with a simple trick, the water test. A splash of clean water can temporarily simulate a polish, bringing out color and translucency. It's not diagnostic, but it helps prioritize samples for cutting or further testing. Stones that brighten or become semi-translucent when wet are often worth retaining. Still, exposure matters. Stones exposed to harsh sun or acid rain for decades can develop a patina that hides their true luster. That's why a clean break, either from a fresh fracture or a trim saw, is often the fastest way to bypass surface deception. And when that first break reveals unexpected depth, texture, or glow, the question becomes, where exactly did it come from, and what does the terrain say about what might still lie beneath? The terrain doesn't lie, it just speaks a language most collectors never learn. Understanding where valuable stones originate begins not with the rock, but with the land. Ancient heat, buried pressure, and shifting faults that concentrate specific minerals in predictable zones. If a dull stone polishes up with unexpected beauty, the real question is, does the ground match the mineral's geological backstory? Take subduction belts, zones where oceanic plates dive beneath continental ones. These create the extreme pressure temperature regimes that form jadeite, the rarer and more valuable cousin to nephrite. Places like Myanmar, Guatemala, and parts of Japan host these belts. If you're in terrain once marked by deep tectonic compression, especially with exposed blueschist or eclogite facies rocks, jadeite might not just be present, it could be native. In contrast, serpentinized terrains, the remnants of ancient oceanic crust now uplifted, are rich in magnesium silicates and are the natural home of nephrite. California's coast ranges, British Columbia's interior, and parts of New Zealand's South Island all feature these complex greenstone belts. Spotting dark green, waxy stones in these regions should instantly raise suspicion. They might not be just serpentine, but gem-grade nephrite. Volcanic zones tell another story. Opal, for instance, forms where silica-rich fluids fill cavities in cooling lava or weathered tuffs. Australia's Lightning Ridge, Nevada's Virgin Valley, and Ethiopia's Wellow region are prime examples. If you're near rhyolite domes, ashfall beds, or perlite flows with signs of past hydrothermal activity, those dull-looking nodules in the wash could be fire opal in hiding. Garnets, often thought of as common, become significant when they appear in high-grade metamorphic rocks like schists and gneisses. Their presence alongside staurolite or kyanite suggests the right conditions for gem-grade crystals. Road cuts in Appalachia, certain alpine terrains in Europe, and the Mozambique belt in Africa all yield valuable garnet rough, if you know what to look for. And then there's the river logic. Paleochannels, meanders, and countercurrents. These don't create the gems but concentrate them. Heavy stones like sapphire, diamond, and zircon settle out in slow spots, inside bends, behind obstructions, or where gradient suddenly changes. If you're in an area geologically suited to hosting gems, these secondary deposits, known as placers, are often where the highest concentration finds occur. So, before testing a stone, test the land. Ask, does this location make geological sense for what I found? Because when terrain and mineral match, the odds of value increase dramatically. But when they don't, it might mean either a rare transport event or a mistaken ID. A rock's surface tells a story, but it's the combination of 5 field signals that whisper whether that story ends in value. Most casual collectors trust their eyes alone, chasing color or shine. But seasoned finders know better. A stone's true potential lies in how it behaves under light, pressure, and touch, especially when cross-referenced with the context of where it was found. The first sign is weight, or more precisely, density. Pick up 2 stones of similar size. The heavier one often contains more than just silicates. Jadeite, for example, feels noticeably denser than quartz. Even without a scale, this heft test starts building suspicion when specific gravity exceeds 2.9. Field-confirmed nephrite can weigh up to 25% more than a same-size piece of jasper. Luster comes next. Not the brightness, but the type of reflection under diffuse light. Quartz and agate flash with vitreous luster, like broken glass. Jade, especially nephrite, often reflects light more softly, with a waxy or oily gleam. Glassy is common, greasy is rare and meaningful. Third is fracture. Smooth conchoidal breaks, curved, like the inside of a shell, indicate uniform crystalline or amorphous structure, typical of silica-rich minerals. Jagged, uneven breaks suggest composite or weathered material. Stones that snap with clean arcs under a hammer strike, or already show natural breaks, are more likely to polish well and reveal internal translucency. Translucency itself, especially along thin edges or chips, is among the most powerful early clues. Hold the stone to the sun. Does light pass through? If yes, even slightly, you've moved into potential gemstone territory. Common chalcedony, moss agate, fire opal, and jade all show translucency before color or structure is obvious. Finally, the context matters. A greasy green stone in a known serpentine belt hints nephrite. A glassy nodule in an ash bed could be opal. A dark, heavy pebble in a river with known garnet schists upstream may deserve a closer look. No trait works in isolation, but together, these 5 create a confidence stack that separates true candidates from scenery. And that stack can be built in minutes using only your eyes, hands, and sunlight. But while these signals open the door, they don't lock the call. Sometimes, the most promising sample still needs a quick test, because a stunning surface can mask a worthless core, while a modest-looking stone can be hiding something far more valuable beneath. Weight in the hand reveals more than color ever could, especially when time is short and tools are limited. It's the most overlooked diagnostic step, yet one of the most reliable first filters for value. Many high-dollar gem materials are simply denser than their common cousins, and the human hand is remarkably good at detecting those differences, if trained to pay attention. Here's how it works in the field. 2 stones of similar volume are picked up, one in each hand. Without even looking, the heavier one will feel noticeably weighted if it crosses a certain threshold, around 3.0 specific gravity or higher. Quartz, for reference, sits at 2.65. Chalcedony and common opal hover near that, too. But jadeite, nephrite, and almandine garnet all push well beyond that point. Jadeite can reach 3.5, garnet even higher. Even in rough, uncut form, the heft difference becomes clear with repetition. Collectors often describe it as a solid or planted feel. Stones that hit this density range tend to sink faster in water, resist casual flipping in a pan, and, critically, feel heavier than they look. That discrepancy is the trigger. A palm-sized chunk that feels too dense to be quartz deserves further testing. And it's not just about feel. The test can be field quantified using basic water displacement. Weigh the stone dry, then submerged, and apply the SG formula, weight in air divided by weight loss in water. Even a cheap pocket scale and a cup of water can get you within plus or minus 0.05 accuracy, enough to separate valuable jade or garnet from common rocks. In riverbeds, this principle becomes even more powerful. Gems that resist transport due to density, like corundum, zircon, and diamond, settle in specific traps. Finding a cluster of unusually heavy pebbles in a slow bend or behind a rock bar often precedes a meaningful discovery. That's why experienced prospectors bring a plastic gold pan, not just for precious metal, but to watch how stones sort by density. But there's a caveat. Some high-density imposters exist. Hematite and magnetite, for example, are both heavy and dark, but lack the luster and fracture patterns of true gem materials. That's why weight alone must always be cross-checked with visual and textural cues from earlier steps. Still, in the early stage of a search, when time is limited and dozens of stones beg for attention, heavier than expected is often the clue that saves a priceless sample from being discarded. A simple splash of water can transform a worthless rock into a potential gem, at least to the eye. Yet that momentary change is often the deciding factor between what ends up in a backpack and what stays behind. The wet test is one of the oldest, cheapest, and most deceptively powerful steps in gemstone identification, revealing color, translucency, and texture that dry surfaces almost never show. In the field, most valuable silicate-based stones, opal, chalcedony, jade, are naturally dull when coated in dust, oxidation, or surface weathering. But the moment water penetrates the fine surface pits and enhances the refractive index, key traits emerge. Common opal, for example, can shift from chalky white to glowing pastel with visible color zoning after a quick rinse. While not diagnostic, this visual change helps prioritize samples. Take moss agate. Dry, it may look like plain brownish quartz. Wet, the dendritic inclusions, iron or manganese oxide formations resembling ferns or moss, suddenly appear, sometimes in stunning green-black contrast. Plume agates, too, reveal feathered structures only visible when the stone is cleaned or wetted. These patterns can command high value when clear and centered in a cuttable zone. Jade, especially nephrite, undergoes one of the most dramatic wet transformations. A stone that looks gray or olive green dry may turn deep green, almost glowing, when water reveals its internal structure. The saturation, evenness, and translucency of this wet appearance often correlates closely with cut value. Buyers in markets from Guangzhou to Vancouver still use water as a first-glance valuation tool before bringing out lights or loupes. Even in volcanic terrains, The water test distinguishes rhyolite from opalized material. Hydrated silica nodules, common opal, show a waxy shine and may transmit light when wet. True rhyolite stays opaque and coarse. This trick is especially useful in perlite or ash flow regions where opal fills voids unpredictably. But there's a danger. Water can temporarily mask flaws. Fractures, pits, and cloudiness often disappear under a wet sheen, only to return once the stone dries. That's why professional graders rely on both dry and wet views before cutting. In the field, it means that while water is excellent for screening, it shouldn't be the final decision point. A $5 magnet can do what hours of visual inspection often can't: flag stones that have a hidden link to precious minerals. Most field collectors overlook this tool, assuming magnetism is for metal detectors or gold hunters. But in gem prospecting, magnetite and ilmenite are more than just heavy black grains. They're mineral indicators tied directly to diamond, corundum, and even rare garnets. Here's the logic. Certain ultramafic rocks, like kimberlite and lamproite, are known diamond hosts. These pipes form deep in the Earth's mantle and punch upward, bringing up diamonds and associated minerals. Among those associates, magnetite, ilmenite, and chromite. They're denser than typical sand and have weak to moderate magnetic response. If your pan concentrates include small black grains that jump or twitch toward a neodymium magnet, you may be standing in a terrain that's hosted deep-sourced eruptions. To test, pass a strong rare earth magnet just above the surface of your heavy mineral concentrate. Tiny metallic grains will twitch or shift. Ilmenite often gives a delayed but observable pull, unlike non-magnetic garnet or zircon. Sorting magnetics from non-magnetics is step one in zeroing in on potential kimberlite indicators. But this isn't just about diamonds. In sapphire-bearing terrains, like Montana's Yogo Gulch or Sri Lanka's gem gravels, magnetite and ilmenite often appear downstream from corundum sources. While sapphires themselves are not magnetic, their associated matrix rocks often are. That means a concentration of magnet-responsive heavies raises the chance that adjacent or upstream deposits contain something more valuable. It's not foolproof. Many iron-rich rocks are magnetic without holding gem potential. Basalt, for example, can produce abundant magnetite but little of value. That's why context matters. If magnetic minerals appear in a setting with serpentinized rock or ancient volcanic conduits, the signal becomes significant. There's also an inverse application. If a bright, heavy-looking stone doesn't react at all, and occurs in a magnetic-heavy zone, it may be non-metallic and thus worth keeping. Moissanite, a diamond simulant, can be electrically conductive but not magnetic. Real diamond, neither magnetic nor conductive. The magnet, in this case, helps narrow the field of suspects rather than confirm identity. The thermal conductivity tester, commonly called a diamond tester, offers a yes or no response in seconds. But interpreting that response correctly is where amateurs often fail. While these devices are marketed as diamond detectors, their real value lies in how they eliminate pretenders and flag materials that conduct heat differently from surrounding rocks. Here's how they work. A heated probe touches the stone surface and measures how quickly heat is drawn away. Diamond, with its unparalleled thermal conductivity, cools the probe so fast the tester emits a high-pitched beep or flashes a diamond light. But high readings aren't exclusive to diamonds. Moissanite, silicon carbide, also scores high, sometimes triggering the same alert. So do synthetic materials and some thermally engineered fakes. That's why field users pair thermal testers with electrical conductivity checks, especially when moissanite is a concern. Real diamonds are electrical insulators. Moissanite often conducts electricity. Some advanced testers combine both thermal and electrical probes, offering a dual-pass check. If a stone conducts heat but not electricity, it leans diamond. If it does both, moissanite is more likely. In the field, this device can quickly dismiss quartz, glass, or zircon, all of which conduct poorly and won't trigger a high reading. This makes it ideal for river or glacial contexts, where bright, clear stones are abundant but most are worthless. A single pass of the probe helps sort rough material and prioritize samples for further verification. But the tester has limitations. It won't identify colorless sapphire, corundum, which has moderate thermal conductivity but often falls below the device's sensitivity. Nor will it help with jade, garnet, or opal, all of which conduct poorly and are misread as not diamond. That's why knowing when not to use the tester is just as important. It's a great discriminator in diamond contexts, not a universal gem reader. Surface conditions also matter. Dirt, oil, or even finger moisture can skew results. Stones should be cleaned and stabilized before testing. Uneven surfaces or high curvature can cause probe slippage, giving false negatives. And very small stones, under 0.10 ct, may not have enough mass to register a reliable reading at all. But in the right terrain, with the right material in hand, thermal testers are a powerful shortcut. They've confirmed many field finds that otherwise would have been dismissed as quartz. And once a stone passes this test, the next question emerges: what else is it hiding? Because even stones that seem promising can emit light in ways that raise new questions. Ultraviolet light reveals what the sun never could: internal structures, trace elements, and treatments that are otherwise invisible. Yet despite its simplicity, the UV test is often misunderstood. Many collectors believe that if a stone fluoresces, it must be valuable. The truth is more complex. Fluorescence under UV isn't a guarantee of worth, but it can be a powerful indicator of authenticity, alteration, or even fraud. Start with the basics. Most field kits use long-wave UV light, 365 nanometers, which is safer and more widely applicable than shortwave. Under this light, certain minerals glow due to electron excitation, common in stones with trace activators like manganese, chromium, or uranium. Diamond, for instance, often fluoresces blue under long-wave UV. About 30 to 35% of natural diamonds show strong to medium fluorescence, with the rest weak or inert. But beware, some synthetics and simulants fluoresce even stronger. Moissanite, a popular diamond simulant, can fluoresce yellow-green, instantly distinguishing it from a blue-flashing natural diamond. Cubic zirconia may show no reaction or a dull white glow. Some glasses fluoresce weakly or unevenly. That means fluorescence isn't a diamond test. It's a differentiator when paired with thermal or electrical checks. Fluorescence also plays a role in jade identification. Jadeite, when untreated, rarely fluoresces. But if the stone has been polymer impregnated, type B jade, or dyed, type C, it often lights up under UV, especially with greenish or whitish tones. This makes UV light a critical fraud filter, particularly in markets where jade is sold in rough nodules or slabs. If a green stone glows unnaturally, it's almost certainly been altered. Opal tells yet another story. While most precious opal doesn't fluoresce strongly, some varieties, particularly white opal and common opal, can show green or blue glow. Synthetic opals can be flagged this way too. Some exhibit a rigid, repeating pattern of fluorescence not found in natural stones. And then there's scapolite, fluorite, and scheelite, minerals that are barely noticeable in daylight but blaze violet, blue, or yellow under UV. In rare cases, these fluorescing finds turn out to be more valuable for their collectability than their cut potential. But perhaps the most deceptive signal is bright fluorescence in worthless quartz. Certain quartz varieties glow intensely under UV due to natural irradiation or rare earth elements, causing many hopeful collectors to mistake them for diamonds. Without thermal and SG tests, this false positive can derail a promising lead. The rule is simple: fluorescence suggests a story, but doesn't write the ending. It helps spot treatments, separate fakes, and flag unusual chemistry. But once a stone passes, or fails, under UV, the next step isn't lab work. It's about what happens in the field next: sorting, concentrating, and recording the finds with precision. The most valuable stone in a field bag is worthless without process. That's why experienced prospectors don't just collect, they grid, concentrate, and record. Without this discipline, promising material becomes impossible to relocate, test sequences can't be trusted, and any real discovery risks being unprovable. What separates a lucky finder from a repeatable method is simple: the field workflow. It begins with grid sampling. Using GPS or topographic overlays, a site is divided into manageable cells, often 5 by 5 or 10 by 10 meters, depending on terrain. Each cell is scouted for signs: mineralization, heavy concentration, or float stones with desirable traits. Samples are bagged by grid square, not just tossed together. This one practice makes lab verification, resale, and even scientific interest possible. A stone without location is just a curiosity. A stone with coordinates is data. Once samples are tagged, the next step is concentration. Whether in streambed, tailing pile, or weathered slope, the goal is to isolate high-density material. Sluice boxes, battue pans, or dry sieves serve this function. A basic sluice with ripples can separate heavy black sands, magnetite, ilmenite, from lighter matrix. A number 20 mesh sieve, almost equals 0.85 mm, can quickly sort out fine gravel from silt. As heavier grains concentrate, visual sorting becomes easier and more precise. Collectors often follow this with a clean pan sweep, washing the concentrate until only heavies remain. From here, tweezers and a hand lens isolate candidates, tiny garnets, zircons, sapphires, even microdiamonds. Any cluster of indicators in one square triggers a higher density sample or extended dig. This feedback loop drives the process forward intelligently, not randomly. And every step is documented. GPS coordinates, photo logs, field notes. What test was run, what was seen, what was discarded. This matters not just for personal records, but for potential sale. Buyers of rough, especially jade, opal, or diamond, want provenance. A verified origin increases price and trust, while undocumented material often gets lumped into commercial grade or rejected altogether. Even small steps, like using plastic instead of metal tools, can preserve clarity and avoid contamination during sorting. Keeping water separate for each site prevents cross-sample artifacts. Label everything: bags, vials, even photos. And when a stone passes enough of these workflow steps, luster, weight, fracture, UV, and grid-confirmed context, it earns the right to the next level of scrutiny. But even then, not every stone tells the truth. Some pass every field test, until they don't. It looked perfect, translucent, dense, glossy, even satiny along the fracture. The stone had all the markers: weight, luster, context, and a clean scratch test at over 7. For all practical purposes, it seemed like jadeite. But under magnification and acetone, the illusion fell apart. The specimen was a classic false positive, a dyed, wax-filled serpentine sold as jade, a common fraud that plagues both markets and field collectors alike. The error began with overconfidence in surface traits. Serpentine and nephrite can be nearly indistinguishable at first glance, especially when serpentine is finely grained and polished. Both can show olive to deep green color, a waxy surface luster, and a dense feel in hand. Though serpentine is slightly lighter, Sg is almost equal to 2.5 to 2.6 versus nephrite's 2.9 to 3.0. But serpentine fails under hardness testing, usually scratching at 5.5, while nephrite resists steel. In this case, weathering on the sample made hardness inconclusive. The cut face polished up beautifully. Under wet light, it had the soft green glow sought in low-grade jade. But a field acetone test, a few drops on a cotton swab, then rubbed on the stone, pulled faint green dye. Under long-wave UV, faint green fluorescence also appeared, inconsistent with untreated nephrite or jadeite. The final blow came from a loupe inspection. What had seemed like fibrous interlocking texture, classic in nephrite, was actually dull and granular, showing sugary surface pitting under magnification. It had been wax-treated to smooth out natural voids, then dyed to deepen color. A textbook example of Type C imitation jade, stabilized, dyed, and passed off as natural. This isn't rare. Even in reputable jade markets, false positives pass multiple field tests before being caught in labs or high magnification review. Glass-filled rubies, heated sapphires, and leaded simulants for tourmaline or spinel behave the same way, passing UV and density checks, only to be outed by polish, fracture behavior, or refractive index. Zircon poses another classic trap. Naturally high in density, Sg is almost equal to 4.0 to 4.7, and sparkle, zircon can easily be mistaken for diamond or topaz in concentrates. But under UV it behaves erratically, and under loupe it shows doubling of facet edges, a telltale trait of birefringence. Its surface also shows abrasion under low magnification, something diamonds never exhibit. Field kits with acetone, loupes, and even a basic digital scale prevent these costly missteps. But the lesson remains: when a stone passes every basic field test, suspicion, not certainty, should rise. Nature rarely makes perfect samples without context. And when one does, that's when it's time to turn to institutional benchmarks, the methods used by labs, museums, and geological surveys, to anchor field success in verified science. No matter how sharp the eye or refined the field process, true verification begins where the samples meet recognized standards. Laboratories, academic institutions, and geological surveys don't rely on first impressions. They rely on repeatable, instrument-driven metrics. And for a collector hoping to turn a promising stone into a verified gem, these are the methods that turn stories into evidence. The Gemological Institute of America, GIA, Swiss Gemological Institute, SSEF, and regional labs like NGTC, China, or AGL, Thailand, apply a hierarchy of tests based on non-destructive principles. The first of these is refractive index, RI, a precise measurement of how light bends inside a stone. It's often measured with a refractometer and a drop of contact fluid, and while it can't be done in the field, it's among the most definitive ways to distinguish lookalikes. Diamond, Re 2.42. Zircon, 1.92. Quartz, 1.54, 1.55. Just this number can split fakes from fortune. Next is specific gravity, SG, more accurately measured in lab settings with controlled conditions and analytical balances. Unlike hand-feel or pan estimates, lab SG tests remove variables like air bubbles or hidden cavities. For example, a jadeite sample reading at 3.32 to 3.36 confirms its species, while anything under 3.00 points to nephrite or worse, serpentine. Then there's spectroscopy. With tools like UV-Vis or Raman spectroscopy, labs can identify trace elements and crystalline structure. These tests reveal the difference between natural versus synthetic sapphire or chrome versus iron-colored tourmaline. They also detect treatments, heat, irradiation, polymer stabilization that don't show up in visual or tactile field checks. Microscopic analysis remains one of the most revealing tools in trained hands. Under 30-60x magnification, internal inclusions tell stories. Growth tubes, fingerprint patterns, two-phase inclusions, gas plus liquid, or needle-like rutile, silk, all point to natural formation. Lab-grown stones often lack these imperfections, or show curved striae and gas bubbles instead, artifacts of their synthetic origins. Even basic X-ray diffraction, XRD, or energy dispersive X-ray fluorescence, EDXRF, scans can identify element profiles. These are how institutions confirm whether jade is jadeite, omphacite, or just microcrystalline albite. They're also how new localities get certified for official gem status. Stones must match known mineralogical standards before any market can accept them. For collectors who hope to sell, cut, or insure a find, having a recognized lab report increases both price and trust. A stone with GIA, AGL, or SSEF verification can command 2-5x more than the same material sold uncertified, even when both are genuine. It's not just about truth, it's about proof of truth. The same mineral, same clarity, same color, yet vastly different price. The reason? Origin. In the gem world, provenance isn't just a footnote, it's a multiplier. Buyers pay premiums for stones from storied or rare locations, and conversely, discount similar material from oversupplied or obscure regions. This region effect shapes everything from jade valuation to sapphire resale, and collectors who ignore it often walk away with less than half the value they expected. Start with jadeite. A bright green cabochon with strong translucency might be chemically identical whether it comes from Myanmar or Guatemala. But stones from Myanmar's Pakant region command the highest prices, often 2-3 times more than Guatemalan jadeite, due to Myanmar's long market history, cultural association, and deeper saturation of gem-grade material. Even untreated, top-grade Guatemalan jadeite struggles to breach price ceilings established by origin bias. With sapphire, the region effect is even more pronounced. Kashmir sapphires, prized for their velvety blue caused by rutile silk, can fetch $10,000 to $30,000 per carat in top condition, despite similar-looking stones from Madagascar or Sri Lanka trading at a fraction of that. Buyers trust region as a signal of rarity, stability, and historical prestige. That's why top labs often include origin determination in their reports. A Sri Lankan stone won't become more valuable by cutting alone, but provenance can. Even opal follows this logic. Black opal from Lightning Ridge, Australia is the global benchmark. Thick body tone, brilliant play of color, stable. Ethiopian opals, though often just as vivid, suffer from higher water content and cracking risk. As a result, Even flashy specimens from Ethiopia tend to be priced 40 to 60% lower than their Australian counterparts. This isn't always about prestige, it can be about rarity. Savorite garnet, mined in limited zones along the Kenya-Tanzania border, owes much of its value to geographic scarcity. If identical vanadium-colored grossular were found in bulk elsewhere, prices would likely drop. And then there's the market perception of origin risk. Stones from politically unstable regions or areas with questionable labor practices sometimes face pricing penalties, even if quality is high. A buyer might hesitate to pay full market for a fine emerald from eastern Congo or a ruby from parts of Mozambique, simply due to export risk or certification difficulties. For field collectors, this all means one thing: record where it came from. If you're lucky enough to pull a promising stone from a known premium terrain, whether it's a California nephrite belt or a historic Montana sapphire stream, document everything. The price difference between green jade and nephrite from the Fraser River, BC, can be hundreds per kilogram. And this cuts both ways. When collectors assume origin doesn't matter, they're easy targets for fraud, and more likely to misread a fine's real market ceiling. Some terrains consistently deliver, and others never will, no matter how promising the stones look. For collectors who want more than just chance, understanding the geological fingerprints of high-potential zones is essential. These aren't just famous regions, they're repeatable systems, where structure, chemistry, and erosion conspire to expose and concentrate gem-grade material. And they exist across climates, continents, and tectonic histories. Start with serpentinized belts. These ultramafic zones are the natural home of nephrite jade, chromite, and accessory garnets. Found in places like British Columbia's Fraser River Valley, New Zealand's Westland, and Northern California's Klamath Mountains, these terrains have one defining trait: greenstone. Where tectonic forces mashed oceanic crust into the surface and water altered olivine-rich rocks, nephrite forms in fibrous, compact veins. A waxy, olive-hued boulder from these zones isn't decoration, it's a lead. Then there are opal-bearing volcanic regions, where ancient ash flows and rhyolitic domes created the conditions for silica to migrate and deposit. The Lightning Ridge black opal fields in New South Wales remain the benchmark, but parallel systems exist in Ethiopia's Wallo Province, Nevada's Virgin Valley, and Mexico's Magdalena fields. Here, opal forms in voids, fossil cavities, cracks, or vesicles, often near hydrated tuff beds. If you're in a rhyolite terrain with known hydration history, every nodule is worth a closer look. High-grade metamorphic terrains, especially those with garnet kyanite staurolite assemblages, are hotspots for gem garnets. The Appalachians in the U.S., Sri Lanka's highland complex, and parts of the Mozambique belt in East Africa all yield almandine and grossular garnets of gem quality. Watch for coarse schists, banded gneisses, and deep red or honey-colored grains in pan concentrates. For sapphire and corundum, the targets are alluvial gravels downstream of known igneous/metamorphic source rocks. Montana's Yogo Gulch, Sri Lanka's Ratnapura district, and Madagascar's Ilakaka fields are prime examples. These gems resist weathering and travel far. Their presence in river traps indicates a persistent source. In these terrains, the game is twofold: find the right gravel trap and trace it back upstream. Kimberlite and lamproite fields, though rarer, are the only known primary sources of diamond. These deep-origin volcanic pipes often weather into soft, yellowish soils with high clay content and scattered indicator minerals. The Kopval Craton in South Africa, Arkansas's Murfreesboro Field, and Canada's Lac de Gras region all fit this profile. Even where diamonds aren't visible, the presence of pyrope garnets, chromite, and ilmenite in pan samples suggests potential. Finally, don't overlook river reworks and paleochannels. In places like Australia's Queensland sapphire fields or California's Trinity County, old riverbeds buried under newer deposits hold higher concentrations of heavy minerals than active streams. Ground-penetrating radar or historic sediment maps can locate these ancient flows, often untouched and wildly productive. What unites these terrains is process: deep heat, focused pressure, slow cooling, or extreme weathering followed by selective erosion. What distinguishes them is how accessible and legal they are to work. Because not every high-potential zone is free to explore. Every promising site carries a shadow risk, and the smartest collectors know exactly when to walk away. While gemstone terrains can offer immense rewards, they're often embedded in landscapes shaped by instability: steep slopes, flood-prone basins, or restricted lands. Ignoring those realities doesn't just threaten the find, it can endanger the person holding it. Flash flood zones are among the most deceptive. Many of the best placer deposits lie in arid or semi-arid washes, dry most of the year, but capable of becoming torrents in minutes. In places like Arizona's agate washes, Nevada opal beds, or Australian gully fields, storms tens of kilometers away can send walls of water downstream with no warning. The visual clue: deep-cut arroyos, scattered driftwood, and imbricated gravels, stones stacked like roof tiles, all indicate recent high-energy flow. If you're collecting in such a wash, the clock is always ticking. Slope instability is another hazard, especially in high-altitude jade or garnet regions. Loose scree, undercut cliffs, and rain-slicked metamorphic faces all carry rockfall risk. In British Columbia's jade fields, slabs of nephrite sometimes weather out on steep grades. Chasing them without safety gear, or solo, is a mistake. Rope protocols, buddy systems, and weather checks aren't overkill here. They're standard. Then there's access legality. Some of the world's richest gem zones are embedded within protected lands, indigenous territories, or private claims. In Myanmar, many jade tracts are militarized. In the US, BLM land can often be collected on, but patented mining claims cannot. Even riverbeds are tricky. The bed may be public, but adjacent access may not. Always verify land status with cadastral maps or mineral rights databases. A promising boulder on the wrong side of a fence isn't worth the fine, or the firearm greeting. Wildlife adds another layer. Venomous snakes are common in hot terrains rich in chalcedony or opal. Bears and cougars roam jade and garnet belts in North America. Even bees and wasps can swarm unexpectedly from under stone piles. Knowing regional fauna and keeping noise levels up during approach can prevent most encounters. The difference between a guess and a reliable confirmation doesn't always require a lab, but it does require consistency. Experienced collectors know that field tests, when applied carefully and repeatedly, create a verification plan that narrows risk and highlights which stones are actually worth sending for formal analysis. The goal isn't to replace laboratory testing, but to approach it only when the field evidence already supports the investment. It begins with checking whether the find is repeatable. If one promising stone comes from a specific location, go back and sample the surrounding area. If similar stones with the same weight, luster, and hardness appear nearby, that consistency suggests a real deposit, not a one-off fluke. This is especially important in riverbeds or slopes, where erosion concentrates certain minerals. Repeating the find confirms that it wasn't just chance. The next step is to use the same testing conditions every time. This means the same tools, the same light, and the same handling methods. If one stone feels heavier and resists a steel scratch, and another that looks identical crumbles or feels light, it's a sign that something's off. Either the first test was flawed, or the second sample isn't the same material. Consistency in tools brings consistency in results. Over time, your hand becomes a kind of instrument. When several stones from the same area all feel dense, show a greasy or waxy surface, hold their color wet or dry, and don't scratch easily, you're building a pattern. This pattern, repeated across multiple samples, is more trustworthy than any single test. It becomes your field fingerprint for that stone type. At that point, the question is whether it's worth sending a sample to a gem lab. That decision depends less on excitement and more on evidence. If the stone meets multiple strong indicators, high specific gravity, scratch resistance, clean break patterns, promising luster, and comes from a location known for producing that type of material, then it's probably worth the cost of a lab report. For jade, opal, or diamond candidates, especially, certification can dramatically increase value. But when a sample fails under repeat testing, if it looks the part but reacts to acetone, or if its weight doesn't hold up to a water displacement test, there's little point in paying for lab work. The smart move is to retest or discard, not commit. Stones that survive the gauntlet of field testing, weight, luster, fracture, UV, and grid repeatability, earn their place at the table. But to seal the call, side-by-side comparisons provide the final proof. These aren't flashy tests. They're tactile, visual, and quietly decisive. When done correctly, they remove lingering doubt and settle the question of whether a specimen is genuinely gem-worthy. Start with the slab. Cutting a sample with a lapidary saw reveals internal structure and color uniformity in a way no surface inspection ever could. A rough, green stone may seem promising, but one pass through the blade can show a cloudy, fractured core, or, conversely, a beautifully translucent body with minimal flaws. This is where the best stones emerge, and where most fakes or low-grade materials fall apart. Polishing follows. A cut face taken through a polishing sequence, starting with coarse grit and finishing with cerium or aluminum oxide, tells you whether the material can take and hold a shine. Nephrite polishes to a waxy glow. Jadeite, if genuine, takes a harder glassy polish. If the surface stays dull or pits emerge, the material may be serpentine, not jade. If fractures pull polish unevenly, it's not worth cutting further. Next comes the scratch comparison. Using a known piece of quartz or a simple carbide point, a suspect stone can be tested against a reference sample. If both show resistance, both may be candidates. But when your promising piece scratches quartz yet shows no marks in return, it jumps to the next tier of confidence. Likewise, a fake that powders or flakes under pressure becomes instantly disqualified. This direct, controlled comparison takes seconds, and often settles hours of uncertainty. Water displacement gives the final weight-based signal. When comparing specific gravity between two samples, say, a known jadeite and a new field specimen, the difference becomes obvious. The jadeite should sink faster, feel denser, and displace less water for the same mass. When a new stone matches this behavior within a close range, the argument for similarity strengthens. When it doesn't, the discrepancy raises red flags. Taken together, slab, polish, scratch, and weight, these side-by-side tests don't just confirm the specimen. They refine your eye. Each time you handle a proven sample, your intuition improves. And the next time you find one that looks almost right, you'll know exactly how to test it and what to expect. With the stone verified, the question shifts from, is it real, to, what now? Whether you keep it, cut it, or sell it, the next step carries consequences: economic, emotional, and strategic. Each path opens a door, but it also closes others. Choosing well means understanding what each outcome involves, and what kind of value you're really holding. Keeping a verified rough stone may seem the most conservative choice, but it's often the wisest in the short term, especially when the market for the material is volatile. Jade, opal, and sapphire all experience seasonal and regional price shifts. Holding a rare specimen with lab-backed provenance gives you the option to wait for a stronger market or a better buyer. Displaying the stone, particularly if it has an exceptional texture or pattern, can even build its story, something collectors and buyers pay attention to. But the downside is clear: rough material isn't liquid. It doesn't generate income unless it's sold or worked. Cutting the stone adds immediate value, if done properly. Cutting reveals flaws, shows color zoning, and finalizes potential. For jade, it's the polish and translucency that define top tier. For opal, it's orientation, where color plays best under light. For sapphire or garnet, it's clarity and cut symmetry. But cutting requires skill, risk, and cost. A poor orientation can ruin a valuable piece. One internal fracture can waste half the weight. That's why many collectors partner with lapidaries for shared profit, rather than attempting it solo. The upside is real. Cut stones often sell for 2-10 times more than their rough equivalents. But once cut, you can't go back. Selling the stone, whether rough or cut, turns potential into cash, but it requires proof, positioning, and protection. Proof comes from lab certificates, field notes, and side-by-side tests. Positioning means knowing where and how to market the material. Rough jade sells better in Asia. Fire opal finds buyers in North America and Europe. Garnet often moves through regional fairs or online platforms. Protection means not getting lowballed or scammed. A buyer offering 20% of market value on the spot may know more than they're letting on. That's why even rough stones should be priced against comparables and never sold under pressure. There's a fourth option: partnering. Some finders choose to license access to the terrain or split profits with buyers, cutters, or exporters. In jade and opal zones especially, partnerships are common. One party supplies material, the other processes or markets it. If you've mapped your find properly and can show repeatable yield, that data itself becomes a form of capital. It's not just the stone that has value. It's the process behind it. Whatever the path, what matters most is this: decisions made after confirmation shape the entire legacy of a find. Some stones become heirlooms. Others become income. And some unlock even more. Topic 19. It doesn't matter how real the stone is, if you don't know its value, someone else will set it for you. This is how thousands of collectors lose out every year, through lowball offers, quick buys, and misinformation, often disguised as help. The gem trade, especially at the rough and uncut level, is full of traps that exploit excitement and inexperience. The most common: underpricing. Roadside buyers, small dealers, or online brokers often approach sellers with friendly confidence, asking what you want for a piece. Say a number too low, and it's done, no counteroffer. Say a number too high, and you'll hear vague dismissals, "That's not real jade," or "This color's not in demand." Without your own market comparisons or lab data, you're negotiating blind. One of the oldest tricks is claiming treatment or fraud where none exists. A buyer might say your opal is unstable or that your jade has been dyed, just to justify a lower offer. If you can't counter with test results or origin data, you lose leverage. That's why a simple field verification sheet, SG, UV, scratch test, photo log, can protect value even before a lab certificate is in hand. Another trap is bundling. A buyer will offer a lump sum for a full batch of rough, convincing you it's all low grade. But if even one stone in that group is high quality, the entire bundle becomes profitable for them, and a missed payday for you. The antidote is to separate, test, and price your stones individually whenever possible. Keep the best out of bulk deals unless you're sure. Then there are cutting offers, where someone says they'll cut and sell the stone, then share profits later. Unless this is a written agreement with clear pricing tiers, it often leads to disputes. The cutter may return flawed stones, claim they cracked in the process, or simply disappear. If you go this route, work only with reputable lapidaries and keep samples documented before and after. The worst-case scenario is when you accept payment far below value and watch the same stone resurface, cut, certified, and sold for 10 times what you were paid. This isn't a rare story. It happens in nearly every gem market where rough material changes hands. And it always happens for the same reason: the seller didn't know what they had. Avoiding these traps doesn't require mastery, it just requires preparation. Know the basic price bands. Learn what labs cost and what they certify. Take time to compare stones online or at shows. And above all, don't sell in a rush. The moment you walk into a gem market with something common but interesting, you become a target, especially if the stone is better than it looks. Underpricing is the oldest trick in the book, and buyers rely on one thing above all: your uncertainty. It's not outright theft. It's a calibrated bet that you don't know what you're holding, or what it's really worth. This plays out across roadside tables, small-town fairs, online message boards, and even inside licensed shops. A buyer inspects your piece, a green translucent stone from a serpentinized zone, or a rough opal nodule with subtle play of color, and offers cash. Fast, friendly, no paperwork. Maybe it's $50, maybe $500. And because you've never sold jade or opal before, it sounds fair. But that same stone, properly verified, might sell for 10 times that, or more, depending on size, origin, and treatment status. The catch is simple: rough material with uncertain provenance or incomplete testing gives buyers all the leverage. They'll cite market uncertainty, possible treatment, or lack of demand to push the price down. And unless you counter with lab reports, SG numbers, and recorded location, you have no leverage. This is especially common with jade. Type A nephrite or jadeite sells at a premium only when it's proven to be untreated. Without a certificate, or worse, if it's cut and polished without testing, it may be lumped with dyed or wax-filled material. Opal follows the same trap. Ethiopian opal, which holds water and can crack over time, is regularly used to justify lower offers even when the sample shows solid stability. Color also deceives. Garnets with rich red or green hues may appear premium to the untrained eye, but value varies widely by species. A buyer might identify it as almandine, common, lower value, even if it's tsavorite or pyrope. Without refractive index or SG data, you can't argue. Some buyers don't intend to deceive, but still underpay out of habit. They buy bulk, assume low quality, and offer wholesale rates for what could be retail-grade material. Others are more deliberate. They recognize a true gem and offer a test cut arrangement, only to walk away with your best piece and vanish from contact. The defense is simple. Never sell without understanding what you have. Bring documentation. No regional price bands. Ask for comparisons. If you're offered $100, ask why, not out of confrontation, but information. What are they seeing? What are they not seeing? Buyers respect sellers who speak their language, SG numbers, luster types, terrain of origin. And when you have proof, the dynamic flips. Now, you're not hoping to get paid. You're choosing who gets to buy.